All right, let's talk about one of the most important fundamental data structures in all of computer science, the binary search tree. You've probably never heard its name, but trust me, it's the secret engine that makes so much of our digital world feel absolutely instant. You ever stop and wonder how your music app can pull up one specific song from a library of thousands in just a blink? Or how a giant database can find one customer record out of millions right when it's needed? Well, it's not magic, it's a really, really clever data structure, and the binary search tree, or BST for short, is an absolute master of this game.
So, what is this big secret? It all boils down to one simple but incredibly powerful idea: keeping everything in order. Let's dive in and see what makes a BST so special.
Now, this is not just any old tree with two branches coming off each node. No, it is an ordered tree. And that simple rule you see right there, that's its superpower. For any node, everything to the left is smaller and everything to the right is bigger. It's this property that lets us basically play 20 questions with our data, cutting the problem in half with every single step. And this table just lays it all out, plain and simple. A regular binary tree, it's just a hierarchy. You might have to check every single node to find what you're looking for. It's like digging through an unsorted pile of books. But a binary search tree, now that is an intelligent structure. Searching a BST is like using the library's catalog. It guides you exactly where you need to go, fast.
Okay, so how do we actually use this super organized structure? Well, the two most fundamental operations, searching for something and adding something new, they follow the exact same, really elegant logic.
Searching is so intuitive, it's kind of like a choose-your-own-adventure game. Say you're looking for the number 18. You start at the top, the root, which is 15. Is 18 bigger than 15? Yep, so we go right to 22. Okay, is 18 smaller than 22? Yes, it is, so we go left. And boom, there it is. In just a couple of steps, we've zeroed in on our target. And you know what's cool? Inserting a new number follows the exact same path. You pretend you're searching for the value you want to add. You follow the left for less, right for more rules until you hit a dead end, an empty spot where it should be, and you just plug the new node right in. The tree's beautiful, sorted order is perfectly kept. So searching is easy, inserting's easy, but taking a node out, yeah, that's where things get a little more interesting. You can't just rip a node out of the middle of the tree without thinking about what happens to its kids. We have to think about deletion in three separate cases. Case 1, the node is a leaf, no children. Super easy, you just snip it off. Case 2, the node has just one child, also pretty simple. You just have the parent node adopt its grandchild, skipping over the node we're deleting. But case 3, the node has two children. Ah, that's the puzzle. And this quote right here, it hits the nail on the head. The problem is, if you remove a node with two children, you've suddenly got two orphan subtrees. Who gets to take the old node's spot? You need a replacement that won't break that fundamental left is less, right is more rule. And here is the absolutely genius fix. You don't actually delete the node. Instead, you find its in-order successor. That's just a fancy way of saying the very next smallest number, which is always the leftmost node in the right subtree. You copy that value into the node you want to get rid of. Then you just delete the successor from its original spot, which is now a much easier case 1 or case 2 deletion. It's a brilliant little shuffle that keeps the whole tree perfectly valid. Okay, so binary search trees seem almost perfect, right? They're fast, they're ordered, they're elegant. But they have an Achilles heel, and it all comes down to one critical word: balance. You see, the whole promise of getting to the data fast relies on being able to cut the search area in half at every step. But what happens if the tree isn't branching out nicely? What if it's just a long, spindly line? And this slide says it all. On the left, you've got a beautiful, bushy, balanced tree. Searching that is lightning fast. That's what we call O log n time. But on the right, if you happen to insert your data in an already sorted order, you get this sad, lopsided thing. It's basically just a glorified linked list. Your search becomes painfully slow, O n time. You've completely lost that superpower of having the search space. This table just drives that point home. In the worst case, a basic BST is no better than a simple list. And that's exactly why computer scientists came up with self-balancing trees, like the AVL tree you see here. These are amazing. Whenever you add or remove a node, they automatically perform these clever little rotations to shift branches around and make sure the tree stays bushy and efficient.
They guarantee that fast O of log n performance no matter what. Now, self-balancing is a huge step up, but the story doesn't stop there. The basic idea of a BST is so powerful that it's been adapted and tweaked to create all sorts of specialized, truly next-level trees. For instance, check out an augmented BST. The idea here is to store a little bit of extra pre-calculated information in each node. So imagine if every node also knew the size of its own subtree. With just that one extra piece of data, you can start asking really powerful questions and get answers almost instantly.
And that leads us to the order statistics tree. By storing the size of its subtrees, it always knows the rank of every single element. That means you can ask it to find the 5th smallest item, or the 100th smallest item, or any nth item, and it can just jump straight to it. That's something a normal BST just can't do.
And for the world we live in today with multi-core processors everywhere, we have things like lock-free BSTs. See, normally, if two programs try to change a tree at the same time, you have to lock it to prevent chaos, which creates a bottleneck. These incredible trees use atomic operations, changes that are so tiny and fast, they're guaranteed to not interfere with each other. This lets tons of different processes read and write to the tree all at once. It's a huge deal for high-performance computing.
So let's bring it all home. What are the big takeaways? 1. Binary search trees are all about that simple ordering property. Left is less, right is more. 2. Their amazing speed is completely dependent on staying balanced. An unbalanced tree is a slow tree. And 3. This basic concept is so incredibly powerful that it's become the foundation for all sorts of advanced structures that solve some really tough problems.
So now you're in on the secret. Think about it. The file system on your computer that lets you find a file instantly. The autocomplete in your search bar. The way databases index billions of records. Now that you know the principle, I bet you'll start seeing the elegant, powerful logic of the binary search tree absolutely everywhere.